For decades, we've been told that black holes are the universe's dead ends. Cross the event horizon and you're gone, crushed, erased from existence. End of story. But what if that story is wrong? What if, theoretically, you could survive the fall? What would you see? What would you feel? And what would you find at the bottom? In 2026, new research in quantum gravity is rewriting everything we thought we knew about black hole interiors. The inside might not be empty. It might not even be an end. Welcome to the hunt for what lies beyond. First, let's define our monster. A black hole is where gravity becomes so intense that it warps space and time completely. Its boundary is the event horizon, the point of no return. Once you cross it, not even light can escape. Black holes come in two main sizes. Stellar mass black holes are born from collapsed stars, packing up to 20 suns into a city-sized object. Supermassive black holes, like the one at the center of our Milky Way, are billions of times heavier. And here's the first twist. The bigger the black hole, the gentler the entrance. At a supermassive black hole, you might cross the event horizon without even feeling it. The real danger, that comes later. You've probably heard of spaghettification, the idea that your body would be stretched into a long, thin noodle by tidal forces. Your feet feel stronger gravity than your head, pulling you apart like taffy. But here's the catch. This only happens catastrophically in smaller black holes. If you fall into a stellar mass black hole, you'll be spaghetti long before you reach the event horizon. You'd never even cross. At a supermassive black hole, however, the event horizon is so far from the singularity that tidal forces are gentle. You could fall through completely unaware, alive, intact, and falling toward the center. So you've crossed the event horizon. What do you see? The universe above you isn't gone. In fact, you can still see the stars, but they're changing. Gravity bends light, so the entire sky compresses into a shrinking, bright circle above you. Below you, there's no bottom, just darkness. But you're not falling through space. You're falling with space itself. Time and direction have swapped places. Inside a black hole, moving forward in time means moving toward the singularity. You can't avoid it any more than you can avoid tomorrow. This is where physics breaks down. According to Einstein, your journey ends at the singularity, a point of infinite density where spacetime ceases to exist. But Einstein's math doesn't include quantum mechanics, and that's where the new story begins. The singularity is a red flag. Infinite density isn't something nature actually makes. It's a sign that our theory is incomplete. General relativity works beautifully outside black holes, but inside it screams error. To understand what really happens, we need quantum gravity, a theory that merges Einstein's relativity with the strange rules of the quantum world. And in 2026, researchers are making real progress. One leading theory, Horava-Lifshitz gravity, suggests that at the highest energies, spacetime itself becomes quantized, broken into discrete chunks like pixels on a screen. If that's true, the singularity might not be a point. It might be a region. String theory offers another wild idea, the fuzzball. Instead of a smooth horizon and an empty interior, the entire black hole might be a tangled ball of fundamental strings. There's no inside at all, just a fuzzy surface where information is stored. Then there's the firewall hypothesis. Some physicists argue that to solve the information paradox, the event horizon might actually be a blazing wall of high-energy particles that would incinerate you instantly. No gentle crossing, just instant destruction. Which one is right? We don't know yet, but each theory is a clue, a piece of the puzzle in understanding what truly lies at the heart of these cosmic monsters. Here's the core problem. Quantum mechanics says information can never be destroyed. If you burn a book, the information is scrambled, but it still exists in the smoke and ash. But a black hole, according to Hawking, it slowly evaporates into random radiation, taking all information with it. This is the black hole information paradox. It's been raging for 50 years. If information is truly lost, then the universe isn't deterministic. If it's preserved, then something must be happening inside those black holes. Recent 2026 research suggests that information might escape through subtle quantum effects, correlations in Hawking radiation that we're only beginning to detect. Black holes might not be eternal prisons. They might be leaky. If information can escape, maybe other things can too. Einstein's equations allow for wormholes, tunnels connecting two distant points in spacetime. Some theories suggest a black hole's interior might connect to a white hole on the other side, spewing matter out into another universe. In loop quantum gravity, some models predict that a collapsing black hole could bounce, turning into a white hole that slowly releases everything it swallowed billions of years later. You wouldn't just survive. You might emerge into a different time. Are these real? Probably not. Most wormhole solutions are unstable, they collapse instantly. But the fact that mathematics allows them tells us something profound about the flexibility of spacetime. We can't send a probe into a black hole, yet, but we can observe them. The Event Horizon Telescope gave us our first images of black holes in M87 and our own Milky Way. Those images match general relativity's predictions perfectly. Gravitational wave detectors like LIGO have recorded ripples from merging black holes. These ringed-on patterns also match Einstein's math, but they leave room for subtle deviations, tiny echoes that could hint at quantum effects near the horizon. Some researchers are hunting for these echoes now. If they find them, it could mean the event horizon isn't a perfect absorber. It might have structure. It might be fuzzy. As we probe deeper into these mysteries, one truth becomes clear. The universe operates on laws so precise, so elegant, that they continue to astound us. Black holes aren't chaos. They're laboratories for the deepest rules of reality. In Islamic tradition, believers are encouraged to reflect on the heavens and the earth, to seek knowledge, and to marvel at the signs of creation. The study of black holes is part of that quest, a journey to understand the magnificent order woven into the cosmos. Whether we find fuzzballs, firewalls, or something we haven't imagined yet, one thing is certain. The universe is far stranger and more beautiful than we ever dreamed, and we are just beginning to understand our place within it. The next decade will transform our understanding. The Vera Rubin Observatory will map millions of black holes. LISA, a space-based gravitational wave detector, will see ripples from the dawn of time, and quantum simulations are recreating black hole physics in labs on Earth. In 2024, researchers demonstrated that quantum information can escape an analog black hole horizon in a spin chain experiment. It's not a real black hole, but it proves the physics is possible. We may never physically visit a black hole, but through theory, observation, and simulation, we are building a picture of what lies inside. And that picture is getting clearer every year. So could you survive inside a black hole? The classical answer is no. The quantum answer is maybe. Maybe you'd be encoded in the fuzzball. Maybe you'd emerge in another universe. Maybe you'd become part of the information itself. What do you think? Is there something beyond the event horizon? Or is it truly the end? Let me know in the comments. And subscribe to Tomorrow's Science for more journeys to the edge of knowledge. The universe is full of mysteries, but one thing we know for sure, the search for answers is what makes us human. Stay curious. We'll see you next time.